This video, Material Balance 2, is from the Computer Applications course, but includes detailed solutions to problems 12, 1, and 2 from the CHM 507 Industrial Chem course. The remaining problems are discussed in the video Material Balance 3.
Matrices. Matrix math is described in most pre-calculus textbooks. What's it used for? Well, one of the main uses is to solve systems of simultaneous linear equations. For example, these two linear equations have a point of intersection. You can use matrices as a way of solving for the point of intersection. Just in a general note here, solving two simultaneous two-variable linear equations will yield a point of intersection, as for example here the point 5 and minus 2 on this graph. Solving three-variable linear equations in x, y, and z will yield a point or a line of intersection of three planes in a 3D volume. So here's a point of intersection of three planes, and here's a line of intersection of three planes. Either of these are possible when we have three-variable linear equations. Solving four-variable linear equations in x, y, z, and w gives a point or a plane or volume of intersection of volumes in a hypervolume, whatever that is, illustrated up here on the right. And systems of linear equations can also be solved using matrix operations, and these are studied in linear algebra courses. We'll solve these equations now using matrix operations in Excel. Page 373. Technologists, engineers, even business people are required to solve systems of linear equations. Chemical equations include material balance problems and deconvolution of overlapping UV-Vis spectra. For example, after taking measurements across a distillation column, the following set of linear equations were generated. Now, don't worry if you don't understand where these equations come from at this point. We'll do this later, but for now, just appreciate I have two linear equations with the same variables in them. Two equations, two unknowns. I should be able to solve them. In these equations, D represents the flow rate of the distillate from the top of a distillation column in kilograms per hour, and U represents the rate of underflow from a distillation column in kilograms per hour. So we have 0.75 D plus 0.02 U is 12, 0.25 D plus 0.98 U equals 88. So to solve for the values of D and U are two unknowns, the student may use the familiar process of rearranging one equation in terms of one unknown, substituting this unknown into the other equation to obtain one equation and one unknown, which is then solvable. Now this process is adequate for simple problems, but for more complex systems of equations involving numerous equations and unknowns, matrix operations are preferred. Now the word matrix, what is that? In chemistry, a matrix is a multi-component chemical mixture or solution, but in mathematical terms, a matrix is simply a rectangular array of numbers. So the coefficients of the constants of a linear set of equations are written in rectangular arrays. 0.75, 0.02, 0.25, and 0.98 are the coefficients of these variables, D and U, and the constants are the values on the right-hand side. So the coefficients and the constants of sets of linear equations are written in rectangular arrays. And then, row by column, multiplications are performed to solve for the variables or unknowns. And these row by column operations, algorithms, just like the process of FOIL in algebra, these are tedious when performed by hand, but can easily be performed by scientific calculators and computer software such as MS Excel. Here's the general process for solving linear equations with matrices. So here are two linear equations. 2x minus y is 12, x plus y equals 3. Two equations, two unknowns, we should be able to solve for the unknowns. What you do is convert the equations into two matrices, two rectangular arrays of numbers. And here's the matrix of the coefficients of the variables, 2, minus 1, 1, and 1. And a matrix of the constants. The constants are 12 and 3. We'll call the matrix of the coefficients A. We'll call the matrix of the constant B. So to solve for x, and x will be the matrix of the unknowns, x and y in this case, here's how that's done. In a general sense, can you agree with me that multiplying a coefficient of a variable times a variable gives a constant? So here we have A is the matrix of the coefficients of the variables. We'll multiply it by x, the matrix of the variables, and we'll get B, the matrix of the constants. If that makes sense to you, and it should at least in a general way, then if we want to solve for x, we would rearrange the equation, divide both sides by the matrix A. We then can say x is equal to a to the minus 1 times b. A to the minus 1 is therefore the inverse of the matrix A. Let's see how this is done in Excel, and then we'll go right there and do it. Here are two variable simultaneous linear equations. We create a matrix of the coefficients of the variables, 2, minus 1, 1, and 1. We'll call that matrix A. We need to multiply the inverse of matrix A, which we get from Excel. This is A minus 1, the inverse matrix of A. We multiply it by B, the matrix of the constants, which are 12 and 3, and it will give us X, the matrix of the variables. Let's see how this is actually done in Excel. This Excel file is called Matrix, and the worksheet is Material Balance. So here are two simultaneous linear equations with two variables. Let's solve for the values of x and y. Let's first create a matrix of the coefficients of the variables. 2, minus 1, 1, and 1. To create the inverse matrix of the coefficients of the variables, first select the cells where that inverse matrix will be displayed. Choose the Insert Function tool. The function you're looking for is called M inverse. Say OK. All you need to do is select the values of the matrix whose inverse you want. Now, in previous versions of Excel, when you wanted to generate more than one value, you could not click OK. You had to click Control-Shift-Enter. But I notice in this most recent version, I can just click OK, and it seems to know that I want 4 values. That's new to me. Alright, so there's the inverse matrix of A. We want to multiply that by the matrix of the constants here, which are 12 and 3. We multiply these two together, and we'll get the matrix of the variables. So select the cells where the matrix of variables will be displayed, and go to the Insert Function tab and find the function called mmult for multiplying matrices together, and say OK. You need to then select array 1, which will be the inverse matrix of the coefficients of the variables, be times array 2, which is the matrix of the constants. Now I know that in algebra the order of multiplication doesn't matter, but for arrays, for matrices, it does matter. You have to enter the inverse matrix of the coefficients of the variables first and the matrix of the constants second. Now I'll simply have to click OK, and yes, it did generate both values. Now you notice that the identity of the variables is not given. I typed in the x and y. So the order in which the variables are listed vertically is the same order that the variables were horizontally in their original equations. So you must keep that in mind. Another constraint you must be aware of is that Excel will only solve square matrices. That is, 2 rows by 2 columns, or 3 rows by 3 columns, or 4 rows by 4 columns. If you try to solve 4 by 3, 3 by 2 or any uneven combination of row and columns, you get an error message. And that's all there is to it. So solving matrices in Excel is an extremely easy procedure. The only difficult part is being able to write the original equations to describe a material balance problem. And we'll get some practice with that. On page 376, we have some practice problems for solving systems of linear equations. Let's do the first one. The feed to a continuous still, that's a distillation column, analyzes by weight to be 28% benzene and 72% toluene. The distillate, that's the overhead product from the still, is found to contain 52% benzene, and the residue, or the underflow from the still, contains 5% benzene. If the flow rate of the feed to the still is 1,000 pounds per minute, calculate to 3 sig figs the flow rate of the distillate and the residue. So the first thing to do with the problem is to draw a diagram that illustrates the mass flow coming in and going out of the system. Let's go to the spreadsheet and take a look at that. This Excel file is called Matrix, and the worksheet is called Material Balance. This diagram represents a distillation column with continuous feed and continuous outflow. In industry, it is normal that the feed to a continuous distillation process is fed at a point where the temperature of the feed is about the same temperature as the liquids in the distillation column, and this least disrupts the process. You don't really need to know this for solving the problem, but I thought I'd mention it in any case. So we're told that the feed rate is 1,000 pounds per minute in total. And we're told also that the feed is 28% benzene and 72% toluene. So that's a simple calculation you can quickly write down the answers to. So 28% of 1,000 pounds per minute gives us 280 pounds per minute of benzene, and then the balance, 72% of the total, is 720 pounds per minute of toluene. The flow rates of the distillate and the underflow are the two variables that we're trying to solve. And I'll use the letter D to represent the flow rate of the distillate and the letter U to represent the flow rate of the underflow or residue. We're told that 52% of the distillate is benzene. We're not told anything else about that, but we could figure out that since there's only two components of the system, and toluene is the other component, then the flow rate of toluene must be 48% of the distillate. So write these percentages as decimals in front of the variable. These decimals are the coefficients of the variables. We can say that the flow rate of benzene in the distillate is 52% of the distillate flow, or 0.52 times D. Similarly, the flow rate of toluene in the distillate is 0.48 times D. For the underflow, we're told that it's 5% benzene, and that's all we're told. So the underflow is represented by the letter U. 5% of that is benzene. We'll write it as a decimal. The flow rate of benzene in the underflow will be 5% of U, or 0.05 U, and the flow rate of toluene in the underflow is the other 95%, and that's 0.95 times U. We now have enough information to solve the problem. Let's write mass balance equations that describe the flow through this system. We can always write the total flow of the distillate, D, plus the total underflow. That's equal to the total flow, which is 1,000 pounds in, must be 1,000 pounds out. So there's one equation with two variables. We simply need one more independent equation with the same two variables. Generally, we can write a mass flow equation for each component in the system. Let's do it first for benzene. So what is the flow rate of benzene in the distillate? We don't know, but it's 0.52 times whatever the distillate flow is. We can write 0.52 times D. That plus the benzene flow in the underflow would be, well, we don't know, but it's 0.05 times whatever the underflow rate is. And together that would be a total of 280 pounds per minute. That's mass balance. The total benzene flow out is equal to the total benzene flow in. Now we can do the same for toluene. What's the flow of toluene from the distillate? We don't know, but it's 48% of the distillate. We can write 0.48 times the flow of distillate plus, what's the flow of toluene in the underflow? It's 95% of the underflow, 0.95 times U. And the total flow of toluene we determined was 720 pounds per minute. So we actually have three mass balance equations that have the same two variables. Pick any two to solve it. Let's take the first two. These values can't be solved by Excel. Excel needs numbers only, not a mixture of numbers and letters. Let's create the matrix of the coefficients of the variables for the first two equations. Just take the coefficients 0.52 and 0.05. For the second equation, 0.48 and 0.95. Now I put a sum function here just as a check. The sum of the coefficients of the distillate flow should equal 1, should equal the total distillate flow. The sum of the coefficients of the underflow should equal 1. It should be the underflow, and in fact they are. Now we need to multiply the inverse of the matrix of the coefficients of the variables times the matrix of the constants. To create the inverse matrix, first select the array of cells where the matrix will be displayed. Then choose the insert function. We want M inverse and say OK. Now just drag over the array of the matrix of the coefficients of the variables and say OK. This A minus 1 is the inverse matrix. We'll multiply this by the matrix of the constants. That'll be the first two values that correspond to the first two equations, 280 and 720. And the sum of these should in fact be 1,000. To get the matrix of the variables, we'll multiply the inverse matrix of the coefficients of the variables times the matrix of the constants. First select the cells where the matrix of the variables will be displayed and choose insert a function mmult. OK. Select array 1, which is the inverse matrix, times array 2, the matrix of the constants, and say OK. And this is the matrix of the variables, 489 and 511. I put a sum function here. It should add to 1,000 because that is the total feed, which would be the total outflow as well, and that works. Now the matrix of the variables are displayed in order vertically in the same order that we've written them horizontally. So vertical order consistent with horizontal order, top to bottom, left to right. And that's it. It's so easy to use. Now it really doesn't matter which two equations you choose. Let's then, just as a check, use the second two equations for the same process. So the second matrix I'm writing is 0.48 and 0.95 and 1 and 1. The inverse matrix, select the 2 by 2 array. We want the inverse of matrix A. Say OK. There's the inverse matrix. Now the matrix of the constants in this case will be the last two equations, 720 and 1000. And the matrix of the variables, select the two cells, insert a function mmult, OK. Array 1 is the inverse matrix. Array 2 is the matrix of the constants, and say OK. We get the same values again. So as you can see, the solving of the matrices is very straightforward in Excel. The only challenge for you really is to set up the problems and write the equations using mass balance. Let's try problem number 2 on page 377. A plant engineer wishes to calibrate the flow meters in the distillate and underflow of a distillation column that is being used to purify methanol in a mixture of alcohols. He asks a chemical technologist, that be you, for assistance. The engineer sets the column feed rate at 100 pounds per minute. The technologist obtained samples from the feed, the distillate, and the underflow of the distillation column and analyzed them by gas chromatography to determine the concentrations shown in the table below. Calculate to 3 sig figs the flow rates of distillate and underflow. Solve this using matrices. So here we have the feed rate is 50% by weight methanol, 30% by weight ethanol, 20% by weight 1-propanol, for a total of 100%. The composition of the distillate is 96% methanol, 2% ethanol, 2% propanol, for a total of 100%. The composition of the underflow is 38.5% methanol, 37.0% ethanol, 24.5% 1-propanol, for a total of 100%. Let's go to an Excel spreadsheet and write some mass balance equations. Notice in this case we have 3 components. We should be able to write 4 mass balance equations, one for each component and then for the total. We still only have 2 variables, so we'll have more than enough equations to solve. Let's go to the Excel spreadsheet and perform this calculation. This Excel file is named Matrix, and the worksheet is called Material Balance. Here's problem number 2. I've drawn a diagram and entered all the data I could from the question. The total feed rate was 100 pounds per minute. It's 50% by weight methanol, that's 50 pounds per minute methanol. It's 30% by weight ethanol, that's 30 pounds per minute of ethanol. And it's 20% by weight propanol, so the feed rate is 20 pounds per minute of propanol. These add to be 100. We don't know what the distillate flow is. We're trying to figure that out. That's one of our variables. We'll just let it equal a variable named D for distillate. For the methanol, we know that it's 96% of the distillate, so we'll say equals 0.96 of the distillate. Ethanol represents 2% of the distillate flow, 0.02 times D. Propanol is 2% of the distillate, 0.02 times D. For the underflow, we use the variable U. We don't know what it is. We're trying to solve for this, but we do know that methanol represents 38.5% of the underflow, so that's 0.385 times U. Ethanol is 37% of the underflow flow rate, 0.37 times U. And propanol represents 24.5% of the underflow flow rate, 0.245 times U. This is all the information we need. We should be able to write mass balance equations. The mass flow out equals the mass flow in. We can write an equation for each component in the system and then one for the total. I've gone ahead and completed all the mass balance equations to save time. Pause the video if necessary, and when you're ready, resume the video and we'll solve for the variables. There are 4 mass balance equations. I'll take the first 2. 0.96, 0.385, 0.02, 0.37. This is the matrix of the coefficients of the variables. We want the inverse of that matrix. I'll select the cells where the matrix will be displayed. Insert a function, M inverse, OK. Here's the address of the array that needs to be inverted, and OK. And now we need the matrix of the constants. Here they are, 50 and 30. The first 2 equations. And we need the product of the 2 matrices to give us the matrix of the variables. Select the 2 cells, insert a function, m multiply, OK, array 1 in this order, inverse matrix first, matrix of the constant second, and say OK. And the values are 20 pounds per minute of distillate, 80 pounds per minute of underflow for a total of 100, and that's consistent. Page 377, problem number 3. The examples we've done so far have been separation problems, distillation as a separation, but you can also solve mixing problems or combination problems in a similar fashion. So the waste acid from a nitrating process contains 23% by weight nitric, 57% by weight sulfuric, 20% by weight water. And this acid is to be concentrated to contain 27% nitric acid, 60% sulfuric, and of course the balance would be water, by the addition of concentrated sulfuric acid, which is 93% by weight sulfuric, the balance would be water, and concentrated nitric acid, which is 90% by weight nitric, the balance of which would be water. Calculate to 3 sig figs the mass of waste acid and concentrated acids that must be combined to obtain 1,000 pounds of the desired material. Let's go to the Excel spreadsheet and work this out. This Excel file is called Matrix, and the worksheet is called Material Balance. Here I've drawn a diagram, entered the information, and done some simple calculations. So the desired product is 27% by weight nitric acid. We're told there's 1,000 pounds of it. Therefore, we write down 270 pounds of nitric acid. 60% by weight sulfuric of 1,000 pounds is 600 pounds of sulfuric acid. The balance must be water. That's 13%. 13% of 1,000 pounds is 130 pounds. These must add to be 1,000 pounds. We're told that the waste acid, I'll use the symbol W for this variable, is 23% by weight nitric. So the content of nitric is 0.23 times W pounds. It's 57% sulfuric, that's 0.57 W. And it's 20% water, and so we'll write 0.20 times W. The nitric acid stream that's being added, we need to know the amount of that, so that's another variable N. It's 90% nitric, so I'll write the nitric acid content as 0.90 times N pounds of nitric acid. And the balance then is 10% water, so 0.1 times N is the pounds of water delivered from this nitric acid stream. The other variable is the weight of the sulfuric acid stream, which I'm calling S. It's 93% sulfuric, that's 0.93 times the weight of sulfuric acid stream. The balance, therefore, is water, 7%, so the amount of water delivered here is 0.07 times the mass of the sulfuric acid stream. So these three quantities combined together will give us 1,000 pounds of this composition. So we can write mass balance equations. We have three variables, N, S, and W, so we need at least three independent linear equations. We should be able to write four, one for the total masses in the system and then one for each component. So I have a nitric acid stream, a sulfuric acid stream, and a water stream. Then I have the components of each stream. So I've written the total pounds of the nitric acid stream would just be N. The total pounds of sulfuric acid stream is S, and the total pounds of the waste stream is W. And those three streams combine together to give us 1,000 pounds. There's one equation. Now let's write a mass balance equation for each component. For the nitric acid, we can say that it represents 90% of the nitric acid stream, or 0.9 N. There is no nitric acid in the sulfuric acid stream, so I write 0 S. In the waste stream is 23% by weight nitric acid, so 0.23 of the waste stream is nitric acid, for a total of 270 pounds of nitric acid in total. So that's the total nitric acid combined together, and this is the total nitric acid in the product. For sulfuric acid, There is no sulfuric acid in the nitric acid stream, so it's 0 times the weight of the nitric acid stream. 93% of the sulfuric acid stream is actually sulfuric acid, so 0.93 times S represents the weight of sulfuric acid delivered by this stream, S. And the waste material is 57% by weight sulfuric, so I write 0.57 times the weight of the waste stream. Together those three masses equal a total of 600 pounds of sulfuric acid. For water, we can write the nitric acid stream is 10% by weight water, so 0.1 times the weight of nitric acid stream is water. The sulfuric acid stream is 7% water, so 0.07 times the weight of the sulfuric acid stream is water. The waste acid itself is 20% by weight water, so I can write 0.2 times the weight of the waste acid stream. Those three masses together represent the total mass of water being combined, and there will give us the total mass of water present in the mixture, and that's 130 pounds. There's four mass balance equations. I'll choose the first three. We simply transpose the coefficients. 0.9, 0, 0.23. For sulfuric acid, it's 0, 0.93, 0.57. Enter. For water, 0.1, 0.07, 0.2. Now the matrix of the constants, we take the first three values for the first three equations, 270, 600, and 130, for a grand total of 1,000. The inverse matrix of the coefficients of the variables, select those cells, insert a function, M inverse, OK. What's the array that we want the inverse of? This 3 by 3 array, and say OK. The matrix of the variables, nitrogen, sulfuric, and water, in order from top to bottom, because they were listed left to right, is equal to M multiply. We multiply the inverse matrix of the coefficients of the variables times the matrix of the constants in that order, and say OK. The values are 193 pounds of the nitric acid stream, 390 pounds of the sulfuric acid stream, 417 pounds of the waste stream combined to give us 1,000 pounds of the specified composition. And I will leave you to solve the remaining two problems, which are very similar to this one.